Morning, everyone. My name is Beckett. I'm from Cape Town, South Africa. I'm a data scientist at Exegetic Analytics. And today I want to give you a lightning run through of spatial optimization with useR in R. So I really love to explore and see new places. And what I wanted to see is what can I see while I'm here in Toulouse? And given my limited time, what can I see within different time intervals? And even better, what can I see with my running shoes on? So we're going to be answering these pertinent questions with the open source routing machine. So useR is a C++ routing engine for calculating the shortest paths between different points in a spatial network. It's open source, it's incredibly fast, especially if you're running a local instance, and it's highly portable. So let's jump right in and see how to spin up our own local instance. So first, get the necessary infrastructure that you need. I did a Linux setup. Then you need to clone the source from GitHub. Then initiate and make the build. This takes some time, so go grab a cup of coffee. And next, install. You can also grab the Docker image for a quick and easy setup. Then we need some data. So head on over to OpenStreetMaps and select your area of interest. For me, it was Toulouse, as you can see here. Click on Export, and then you'll download a rather large XML file. To prepare the data, we then need to decide on what type of transportation profile we're going to be using to determine which routes can and can't be routed along. There are 3 default profiles that come with useR, namely for walking, driving, and cycling, and you can also create your own custom profiles. We're going to use the foot profile for walking times to extract the metadata that we need from the map. The next step is to create a hierarchical data structure that facilitates finding the shortest paths. And lastly, we launch the service so that we can access this API locally. So with the service running, let's test it out. And I wanted to ask the question, how far and how long to walk from here to the capital? This is a screenshot of my terminal, and you can see that I've got a curl request to ping the server. And I've specified the coordinates of our venue here today and the capital, and these are the results. And if we scroll down a bit, you can see that we get the results. The distance is in meters, so it's just over 1 kilometer, and it says that it'll take us about 800 seconds to walk there, which seems about right. But ultimately, we want to actually use this from within R for our optimization calculations, and we have an R package for that. The useR package acts as an interface between R and the useR server that you're either running locally or that you access remotely. There's several functions within this package, and I'll just focus on one today. So if we circle back to my question from the beginning, what I want to do is see what can I see from my Airbnb in St. Cyprian with my running shoes on. And I'm going to do this by generating a series of isochrones. So an isochrone is a line connecting points relating to the same travel time from a central location. If you remember in the beginning, we used the foot profile, but now I want to run. So I created my own custom profile for myself using speeds of on average 12 kilometers per hour, and then extracted the metadata I needed again. So with this new local instance running, what do we do from within R? Well, the first thing to set up is to load our packages, and then we need to point to the server that's running locally. I then set the location of my Airbnb location, and then use the function useR isochrone to generate a series of isochrones from 0 to 30 minutes in 5-minute increments. I then plotted with leaflets, and then I was ready to head out the door. And this is what I generated. And as you can see, the isochrones are in increments of 5 minutes, so I can see from where I'm staying what can I see within certain time intervals? And the color scale definitely helps with perceived level of effort. So, in conclusion, who's coming with me tomorrow morning for a run at 6 a.m.? So I hope you've seen how easy it is to spin up your own local instance of useR, and that once you get into R, it's really fun to start doing some spatial optimization. Thanks.
Hi, I am Peter. I am here to share one story from Trivago with you. First of all, you need to know what is Trivago. Trivago is a website, and we are comparing hotel prices from different websites. So we can ask how we can make money. It's very easy. If you go on Trivago website and click on the right side, for example, xyz.com, you click there, then xyz.com pays money to Trivago, to us. So it's a very nice model for us. So if you go to Trivago and click, we are happy because we make money. And let's say here is a time series for xyz.com for one hotel. And you can see number of clicks per day. On 17th of June, there was over 1,000 clicks. It was a huge anomaly because average number of clicks for a long time was something like 1. So there was increase from 1 to 1,000. You can ask how was this detected, how was this anomaly detected in Trivago? It was not detected at all because we have millions, maybe billions of combinations of hotels and partners. So we don't have anomaly detection on this level. We are running different anomaly detection tools, some with R, but this one was not detected. But this anomaly, it was reported from our partner because they paid a lot of money for it. And they say, hey, this huge number of clicks, but from this 1,000 clicks, nobody booked the hotel. It's bad, it's not typical, we don't want to pay for it. So they said it's fraud. Fraud means these clicks are not coming from humans, but from software. So we gave it to our statistician from fraud department and he said, no, it's not fraud, I am pretty sure. I used R to check distribution of browsers and other technical parameters and also history of these users. And we are sure they are humans. He was right, but this answer was bad. This answer was bad because we have the same problem, yeah? We don't know what happened. So we have too many clicks and no bookings. So we're thinking about it and we say, okay, maybe price on Trivago was bad, was too small. In such case, like people will click more because hotels is cheap, but they will not book because it's, in reality, it's too expensive. But we checked this and also some other things, and everything was fine. But we did some other observation. We checked these sessions, and they were coming from Google. It were a paid session. It means we paid to Google, and we checked, okay, maybe we did some change in some bidding algorithm, which is also like we use R there, but there was no change. So we check. We said, let's check Google Trends. Google Trends is the database, and you can see frequency of how often people are looking for some keywords on Google. So in this case, we can see that ABC Hotel was searched. There was a huge increase for ABC Hotel's Google search on 17th of June. So it explains the huge amount of clicks. So what happened actually? There was a TV show in the UK about this hotel. Then 15,000 people, mostly from Scotland, they went to Google searching for this hotel, then 2,000 clicked on Trivago, and 1,000 clicked on xyz.com. And because they were from Scotland and this hotel is in Caribbean, they didn't book at the same day. xyz.com was not able to investigate it because they are not on Google first page. Trivago is on Google first page. They are not. They have very, very different data and experiences. So what is the learning from this case? For xyz.com, they learned that they can trust Trivago because we were able to explain what has happened and give them proof. For us, we found something new, and maybe we should change something. But why I am here? I am here because we used mathematics, we use R, but much more important was that we understand people, how they behave on the internet. And for example, in this case, we check 5 different databases with 4 different query languages to get data. So typical challenge in our case is we have huge amount of data, but you need to understand which data you should use. And we are hiring. Thanks a lot.
So I'm Angeline, and I'm going to show you how I used R and the tidyverse to draft my fantasy baseball team. So I'm going to start by explaining real and fantasy baseball, and then I'm going to show plots and tables to demonstrate how I used R and the tidyverse to optimize my draft and avoid fandom bias. So let's talk. So baseball is a sport that generates a lot of statistics, but to win, a team only needs to score more runs than the other team. So by contrast, in fantasy, you win with a combination of scoring more runs, hitting home runs, and stealing more bases, etc. So these are called scoring categories, and you want to pick players that are good at these. So I wanted to know which positions contribute more to these scoring categories. It's important because you have to have a player at each position on your team. And it helps to know what order to draft players. Second, how do I rank players so I know who I'm supposed to draft first? So I used R to answer these questions. I grabbed baseball projection data from Fangraphs, which you can see at the bottom, and this predicts how players are going to do in the upcoming season. I also loaded in dplyr and purr for reading and cleaning the data, and then I used the map2df function from purr to read the CSVs in from Fangraphs, and dplyr to pipe and select. So I'm going to start by looking at home runs by position. So I used ggplot2 to make this violin plot. Two things stick out to me here. So the catchers are on the far left, and they're not really good at hitting home runs, and you can tell this by how short their plot is. Outfielders, which are the third plot from the left, are pretty good at them, and you can tell this by the height. So most catchers are also going to hit fewer than 10 home runs based on the width at the bottom, and many more outfielders than catchers will hit more than 30. First and third basemen, which are number 2 and the one on the far right, they're not as good as outfielders, but they're going to hit more than second basemen and shortstops, which are number 4 and 5, who are better than catchers, but only just. So I did the same thing for another category, runs scored, and we see similar patterns. So there's several outfielders that are projected to score over 100 runs, and some first and third basemen. Catchers are, again, going to score the fewest runs, and many of them are going to score less than 25. Second basemen and shortstops kind of fall somewhere in the middle. So the last one that I'm going to look at is RBIs. So we see outfielders again leading the pack, and then third and first baseman right behind them. And catchers, again, fewest RBIs. So it looks like outfielders, followed by first and third basemen, are projected to do better at these scoring categories, and catchers are the worst. So now that I know how to prioritize outfielders and first and third basemen and ignore the catchers, I wanted to know who to draft. So I thought I could find a good baseball summary stat for this, but it turns out for all the stats collected and generated in a baseball game, there isn't a good one to describe how to win my fantasy league. So I went with my own. I created a z-score, which shows how sample measurements will relate to others in the distribution. So without knowing baseball, it's difficult to know if Mike Trout hitting 39 home runs is good, bad, or average. But if I know that the z-score is 2.3, then I know he's more than 2 standard deviations above the mean. So I know that I want to draft him. So this is how I generated the z-scores. I used filter to exclude players with less playing time who might have extreme projections due to small samples. And then I used mutate to make the z-score with the function at the bottom. And then I summed the z-scores to compare the players across all of the scoring categories. So now let's look at these. So I used dplyr's top-end function to return the players with the top 5 total z-scores and then arrange them to sort in descending order. So this helps me prioritize who to draft. And in this top 5 list, it's worth noticing that there's 3 outfielders, which is consistent with what we've seen from their production of runs, home runs, and RBIs. So we learned that I want to definitely avoid catchers and pick outfielders and first and third basemen. And I also learned that we can choose which players to draft by creating our z-score. So this strategy kept me from drafting bad players just because they played for my favorite team, the San Francisco Giants. Thank goodness I used the data instead. So while there are lots of resources for baseball analysis, I decided to start with the tools that I already knew, and I found that the tidyverse was more than enough for exploratory analysis, data cleaning, and plotting my data. So this makes it really easy to translate this analysis to other fantasy sports. So if you want to know more about my exploits with R in fantasy baseball, or if you want to find out how my team's doing this year, go to my website or follow me on Twitter. So last year, I definitely almost came in last, but there's no crying in baseball. So there's room for improvement, and thanks to R in the tidyverse, this year I might actually make the playoffs. Fingers crossed.